All right, what's going on, everybody? So in this video, we are going to look at areas and distances. This is section 5.1 from the Stewart Calculus book. So what we're doing is we have a curve here, and we want to find the area under this curve from some point A to some point B. And here's our function y equals f of x. So how do we do this? Well, the way we're going to start out doing this is we're going to break this area up into rectangles. And we're going to find the area of the rectangles and sum them up. We're going to find the area of each rectangle and then sum those areas up. So let's look at it at an example. So we have an example here. It says use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. All right, and it doesn't say in the problem, but what we're going to do is we're going to use 4 rectangles. All right. We're going to break the area up into 4 rectangles. Now, the best way to do this is to sketch a graph. Okay, just a rough sketch is good enough. So when we graph this thing, we know that's the graph of x squared. And actually, what I'm going to do is I'm going to kind of exaggerate it a little bit, so just so we can have some room, okay, so we can write in there and see what's going on. And of course, you know, it comes on this way too, it goes off that way too, but we're only interested from 0 to 1, so we don't really need this part of the graph. And so we'll say this is 0 and we'll call this 1 over here. And so this is the area that we're looking for, this area right in here. Now, we're going to break this up into 4 intervals, okay, 4 rectangles. So let's draw those in. And I know they don't look the same. They're all supposed to be the same width, okay? All right, now, the first way that we're going to do this, we're going to do this 2 different ways. We're going to do it using right endpoints, and we're going to do it using left endpoints. All right. So right endpoints, that means here, here, and here, and here, we're going to draw our rectangles. And I know that first rectangle is kind of wide, but just keep in mind these distances here, from here to here, here to here, here to here, here to here, they're all the same, okay? They're all the same. I know this one's a lot wider, but I'm not going to take the time to redraw it to get it to look right. All right, so what we're going to do is find the area of each of these rectangles and then sum them up. So what's the area of a rectangle? Well, the area of a rectangle is length times width, or length times width, however you want to call it, okay? So what I need is this width here, and we'll call that width delta x, okay? I need to know what that is, and keep in mind all of the widths are delta x. So the way that we can find delta x is, well, we're going from 0 to 1. So all we do is we find this distance from 0 to 1. So you're going to take this point minus this one and divide it by however many rectangles you're using. And so the width of each rectangle, delta x, is 1/4. That's the width of each one of those rectangles. Now, what do we need? We need the height, okay? We need the height of each rectangle. So I need this value, this one, and this one. See, these are the heights of the rectangle. From the x-axis up to here is the height of this first rectangle. From the x-axis to here is the height of the second rectangle, and so on. Well, all that is what? It's the y values, right? It's the y value. So what would be this y value? Well, see this point here? We got to get this x value, and then we take this x value, plug it into our function, and that'll give us the y value. And then we need this x value, plug it into the function, and that'll give us this y value. That'll be the height there. So what's our x values? Well, from here to here, we know that's 1/4. That's the width. And then we go over another 1/4, and so that x value would be 1/2. And then we go over another 1/4. That would be what? 3/4. And then we go over another 1/4, and that would be 1. So the height of the first rectangle would be y of 1/4, which is 1/4 squared, which is, well, I'm not going to write it out just yet. And then we have y of 1/2. This is the height of the second rectangle. You see that? So that'd be 1/2 squared. And then we have y of 3/4, which would be 3/4 squared. That's the height of this third rectangle. See? Plug in the 3/4, and that gives me this y value here. And then the last one, y of 1, which would be 1 squared. All right. So what's my area? Well, we'll call it R4. That means we're using right endpoints, and we're using 4 rectangles. All right. So that would be the width of the rectangle. Okay, I'm doing the first rectangle now, so it's the width, which is 1/4, times the height, which is 1/4 squared, plus now the area of this second rectangle. The width is 1/4, and the height, we plug the 1/2 in, that's 1/2 squared, and then so on. We'll do the next rectangle. That's 1/4 times 3/4 squared, and then the last one is 1/4 times 1 squared. Make sure I can fit it all on the screen. And then once we punch that into our calculator, we get 0.46875. And there's your area. Okay. Now, that's the area under this curve, an approximate area. And of course, it's not the correct area, is it? It's this area that we found is actually what? It's actually larger than what the area should be, because you see how these rectangles stick out above the graph? See this right here? Let me color that in like green. See this area, this one, and this. See, that's extra. Okay, so we know we're actually over what the actual area is. Okay, all right, now let's do the same thing. Let's find the area again using rectangles, but this time let's use left endpoints. All right, so to do that, let's sketch the graph again. And I'm gonna exaggerate again. So there's 1, there's 0. And so let's break this up. And once again, I know they don't look even, but they're supposed to be. And look, everything's gonna be the same. We've got 1/4, 1/2, 3/4. We know the width, delta x, is 1/4. All this I'm getting from what I did up here. Okay. But this time, instead of right endpoints, we're using left endpoints. So I'm here, 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 and here. And so there's our rectangles. All right. And yeah, look, what's the height of that rectangle? Height of that rectangle is what? 0. You see that? See, it's right here. So we're not even including this area. The only areas we're including is what? Is this area, and this area. So the area we find here is going to be what? Less than the actual area. All right. All right. So we know the width is 1/4. We calculated that, and when we did the right endpoints. Now we need the heights of each rectangle. So this time we're going to this x value, this one, and this one. Okay. And so here we've got y of 0 is equal to 0 squared. That's this one. And then we go here for this rectangle, its height, we plug in the 1/4. So y of 1/4 is equal to 1/4 squared. And then we have the area of this rectangle, we plug the 1/2 in. So that's y of 1/2 is 1/2 squared. And then for the last rectangle, see, we got to plug in the 3/4 to get that height. So y of 3/4 is 3/4 squared. And so our area, and we'll call this L4, left endpoints with 4 rectangles, that's going to be the width of the rectangle times the height plus the next rectangle, the width, which is 1/4, times the height, which is 1/4 squared. See, there's the height we calculated, plus 1/4 times, and then the height of this third rectangle, which is 1/2 squared, and then plus 1/4 times the height of the last rectangle, which is 3/4 squared. And so that's going to give us 0.21875. And you can see, look at the difference. So what we can conclude from this is we can say, so the area, 0.21875, the area is between these two values. That's the area. What's the actual area between those 2 points? Well, we don't know how to find that yet. Okay? We don't know how to find it yet. All right. But we will learn how to do that eventually. Okay? We will actually, if you're watching this video, you might want to watch the next video, the definite integral, and we will actually find the exact area in that section. All right. But this video is kind of introducing us to areas and how to set up to find areas. All right. It's an important section. All right. So let's look at this. All right. So it says the area A of the region S, okay, and this right here, this area here, that's our region S right here, right in there. All right, that lies under the graph of the continuous function f. Here's your continuous function f, okay, that's f, is the limit of the sum of the areas of approximating rectangles. Okay, so that's what we just did. It's telling us we're summing up the rectangles. And n represents the number of rectangles. Okay? But look what this is doing. This is saying the area is the sum of the rectangles. Here's your rectangles. Remember in the previous example we used R4. But we use 4 rectangles. But look, what does it say in here? It's saying the number of rectangles is approaching infinity. See, we're taking the limit as n goes to infinity. So we got an infinite number of rectangles. And all that is the limit as n goes to infinity of f of x1 times delta x. See, isn't that what we did? See how it's using you see it's using the right endpoints here? And, well, look at that. What's this y value right here? It's what? You take this x value and plug it into the function. So that's f of x1. That's your y value. That's the height of that rectangle. And that's what this is. The height of the rectangle times delta x times the width of the rectangle. You see that? And then it just continues on to the next one. The height of the next rectangle. Okay? The height of the next rectangle. And then times the width, and so on. And you have an infinite number of rectangles. All right, that's all this is saying. See, this right here, that's the area of this first rectangle right here. That's this area right here. See that? Plug the x1 in for the height, which is the f of x1, and then times the width. And the width of all the rectangles is delta x. All right. All right, and then we have a note here. It says the width of the interval AB is B minus A. Well, that makes sense. That's the distance from here to here is B minus A. That's how wide that is. So the width of each of the n strips, or of the n rectangles, is delta x equals B minus A, which is this total distance here, divided by n, the number of rectangles. And look, that's what we did up here. All right, so that's what we did right here when we found the width of the rectangle. Except this time, how many rectangles do we have? N, where n is going to infinity. All right. All right, so let's look at this example here. It says, let A be the area of the region that lies under the graph of f of x equals e to the negative x between x equals 0 and x equals 2. And it says, using right endpoints, that word's right, using right endpoints, find an expression A as a limit. Do not evaluate the limit. Okay, we're not evaluating the limit in this one. All right, so basically what we're doing is we are looking for this right here. That's what we're wanting to find. Okay. All right, so let's see what we can do with this. So I've got f of x is equal to e to the negative x. And what I want to do is just kind of maybe sketch this. Just sketch e to the negative x. So if we graph this thing, it's going to look something like this. Okay, that's what the graph looks like. And we're busting this thing up into n rectangles. Okay, and we're going from 0 to 2. See that? 0 to 2. And we have an infinite number of rectangles. I know I've got 1, 2, 3, 4, 5, 6, 7. There's 7 rectangles drawn, but I can't draw an infinite number of rectangles. Okay, but just pretend like we're gonna keep coming in here and adding rectangles, an infinite number of them. All right. So, what do we need? Okay, and remember we're going from 0 to 2. So we need what? We need the width of each rectangle, right? We need the width of each rectangle. So that's this width right here. Well, the width is delta x is equal to what? 2 minus 0, remember, b minus a, divided by the number of rectangles. So that's 2 over n. All right? And so we know from here to here, that's what? That's 2 over n. And then if I go over another, see, this is 2 over n. And this next width is 2 over n. So what would this be? That would be 4 over n. You see that? And then I would have 6 over n. And then I would keep going, and this would be what? 2i over n. Okay, however many times I go over, right? See, this right here, this would be like your x1, x2, x3, and so on. This would be xi. See that? We just keep going. So it's basically, see, 2 times this 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times I, 2i over n, all the way until we get to 2. And we can write 2 is 2n over n. All right, we'll write it as 2n over n. How many rectangles do we have? N. So I'm going 1, 2, 3, ... I, and then I'm going to keep going all the way to n rectangles. You see that? All right. So now let's go ahead and write our formula. So let's write Rn. We'll add the limit in a minute. Let's get this part right here first. Let's get just this. Okay. And then once we get this, then we'll take the limit. Just so we don't have to keep writing so much. So remember, it's, and see, look, and I'm using right endpoints. You see that? So on. Keeps going. So it's what? F of x1, I need the height of this rectangle, f of x1. So it's f of x1 times what? Times the width, times delta x, right? Times this width, delta x. Yeah, I know I haven't put anything in yet. I'm writing the formula out. And then plus f of x2 times delta x. All the width of each rectangle is the same. And then I've got plus all the way to the last one. That's going to be f of xn times delta x. All right, so there's Rn. Now let's go ahead and plug all this in. So Rn is equal to, so what's f of x1? That's 2n, right? See, that's 2n. So I'm going to take the 2n and I'm going to plug it in for x into our function, right? We're evaluating this function at each one of these x values. So I'm going to take the 2n and plug it in for x. So that's e to the negative 2n, all right, times delta x, which is 2 over n, plus, and then we need this next rectangle. You see that? And what is that? That's when x is 4 over n. So I'm going to take the 4 over n and plug it in for x. So that's e to the negative 4 over n times the width, which is delta x. And we're going to do that all the way to f of x of n. So now I'm going to plug this one in. So that's going to be e to the negative 2n over n times the width, which is 2 over n. So there it is. Now, let's make this a little better, okay? So let's take this let's take this 2 over n and let's factor that out. So I'm going to get Rn is 2 over n times e to the negative 2 over n plus e to the negative 4 over n plus all the way e to the negative 2n over n. Right. And now I think we're ready to find the limit. All right, so the area is the limit as n goes to infinity of 2 over n times e to the negative 2 over n plus e to the negative 4 over n all the way to e to the negative 2n over n. And then obviously we can write this a little better. We can write this right here neater. So let's write this as a equals the limit as n goes to infinity of 2 over n. Now this is just a sum, right? We're summing this. And how do I get from this term to the next one to the last one? Well, I'm just going to sum from I equals 1 to n to the last term. Now, what would the formula for each one be? Well, remember, we did it right here. So that would be 2i over, e to the negative 2i over n. All right, and this would be your formula. All right, so I hope that all made sense, but this is what they're wanting to find for this part here. Using right endpoints, find an expression a as a limit. All right, so this would be your answer right here. All right, now there's a part B to this problem also. Now it's telling us estimate the area by taking sample points to be midpoints, and that should be and using 4 subintervals. All right, so this, we're going to do the same problem. We've got f of x is equal to e to the negative x. All right, and on the interval 0 to 2. So this problem here is like the first two we worked. Okay, they're telling us to use 4 rectangles. And that's what we did in the first problem. But remember, the first problem we did what? We did left endpoints, we did right endpoints. And now for this one, we're going to use the midpoint of those rectangles. I know the function's different, but it's still the same process. Okay, it's still the same process. All right, so let's go ahead and sketch the graph. Okay, I think I'm going to put the graph over here. And so this graph's going to come in here like this. And we're going from 0 to 2. And we are doing 4 rectangles. And I know these things are wide, but I like to go ahead and make them wide so I can write in there. Okay, exaggerate it, or you're going to be all cramped up writing stuff in there. All right, so we need what? We need the width of the rectangles. So that's going to be what? B minus A over how many rectangles? 4. And so this is 1/2. So the width of each of these rectangles is 1/2. All right. So I know this is 1/2. This would be 1, and this would be 3/2. See, I'm just going over 1/2 each time. Now, what did it say to use? It didn't say use left endpoints. It didn't say use right endpoints. Okay, it didn't say that. It said use midpoints. So we are going to be, and I'm going to do this in a little bit different color. So we are going to the midpoint of each interval. See that? And I need these values here because look, let's draw our rectangles in there. There's our rectangles right there. Okay. So to get the height of this rectangle, I need to evaluate the function at this x value. To get the height of this rectangle, I need to evaluate it at this x value, and so on. So what would this be? Well, it's halfway between these 2 points. That would be 1/4. You see that? And then halfway between these 2 points would be 3/4. And then 5/4. And then 7/4. Now, how do you get those midpoints? Well, remember, you like this one, 1/2 plus 1 is what? 3/2. And then multiply that times 1/2 gives you the 3/4. See, remember I don't know why I'm showing you all this. Y'all should know how to do it. So that's 3/2. And then take the 3/2 times 1/2, and that gives you the 3/4. And there's that midpoint. Okay. All right. So now, what do we have? Well, now we can find our area. So the area for the midpoint, I'm going to come down here and do it. So the area for the midpoint, and I'm going to use M4. That tells me it's find the area using midpoints with 4 rectangles. So we know delta x is 1/2, right? And so now I need the height of each of these rectangles. So what's the height of the first rectangle? Well, that's what? E to the negative 1/4, right? What do? I take this 1/4 and I plug it in here. That's all I'm doing. I'm not showing my work like I did in the first 2 examples, okay? So I'm taking the 1/4 and I'm plugging it into here. That's giving me the height of this rectangle, and then times the width. And now I need the area for the second rectangle. So I'm going to take the 3/4, and I'm going to write the function right here. F of x equals e to the negative x. So I'm taking the 3/4 and I'm plugging it in for x. So that's plus e to the negative 3/4 times the width of this rectangle, which is 1/2, plus, and then the next one, e to the negative 5/4 times the width, plus e to the height of the next one, negative 7/4 times the height. Times the width. And when we do that, that is going to give us the area is 0.8557. And there's your answer. All right. So right there, using rectangles, you know 3 different ways to do that now. You know left endpoints, right endpoints, and midpoints to find these areas. Okay. All right. So now let's look at this last problem. So we've got a word problem here. Okay. We got a word problem. So it says, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them in the following table. So you're driving down the road in your car, and you take that initial time. That's at time t equals 0. That's this 0 here. And you look at your speedometer and it says 17 miles an hour. And then 5 seconds later, you look at your speedometer again, it says you're going 21. And then after another 5 seconds, which is 10 seconds from the initial time, you look at your speedometer and it says 24 miles per hour. And you do that for 30 seconds. Okay? And they want to know and we want to estimate the distance driven. We want to know how far did we drive, the distance. Well, what do we know? We know that distance is rate times time, all right? Rate times time. And so what do we have here? Well, we can draw this out. And let's see, let's go 5, 10, 15, 20, 25, 30, 35, 40, 45. Let's see. We're going to keep going. 45, and let's go on up here to 50. And then we've got, I know down here we're going to have 5, 10, 15, 20, 25, 30. 5, 10, 15, 20, 25, 30. All right. So what we've got here is this axis here is our time, right? This is our time, and this is our velocity, the y-axis is. Now, remember, this over here, this is in what? Miles per hour. But our time is in seconds. So we're going to have to convert. We're going to need to convert the velocity. So let's draw us another one. So we're going to need velocity, and we're going to do it in feet per second. Okay? We're going to convert the velocity to feet per second. That's typically what you see, and we can calculate the distance based on that. That's typically what you see. You'll see miles per hour, or you'll see feet per second. And since our time is in seconds, we're going to convert it from miles per hour to feet per second. Now, do we know how to do that? Well, let's just convert this first one. So we've got what? 17 miles per hour times what? Now we need, instead of miles, we need what? Feet. So I need to cancel the miles out. So I know 1 mile is 5,280 feet. And then I need to cancel the hours out. So I know 1 hour is what? 3,600 seconds. And so once you do all of that, you end up with your velocity being 25, and this is in feet per second, so that's 25. And so you would need to do that for each one of those. Okay? You would need to do it for each one. And I'm not going to show the work on it. I'm just going to write the answers down. So that would be 31, 35, 43, 47, 46, and 41. And so we'll do this as 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All right. Now, let's plot these points. So keep in mind this point here that's 0, 25, 5, 31. So this is the point 0, 25, 5. Whoop. This is the point 5, 31. This is 10, 35, 15, 43. See, these are the points I'm going to plot. 20, 47, 25, 31, and 30, 41. So all I'm doing is plotting those points, these points here, and that's where I get them. 0, 25, 5, 31. See, I'm not using this line anymore, okay? Because that's my velocity, but I'm using these velocities in feet per second instead of miles per hour. So let's plot these. So let's see, we've got 0, 25, 5, 31. I'm going to estimate them the best I can. 10, 35, 1543, 2047, 2531 is about right in there, and then 3041 is about right in there. Is that right? Oh, wait a minute. No, that should be 46. I wrote that 31 down. That should be 46. So 2546 and then 3041 is about right there. And so you can see this is what I have. And so what this does is I can break this up into rectangles, and I can I'll use left endpoints here. Okay. So it's going to look something like that. I think I drew that right. Well, actually the 25, this point right here should be up a little bit higher than this point. This point ought to be a little bit lower. And then here we're down here at 41. So it's kind of coming like this. And so anyway, okay, we're somewhere like that. It's just a rough sketch. Now, I guess this should have just kind of really come this way more, and it'd have been like that. Anyway, now let's find the area. Well, we know the width of each of these delta x is 5. That's the width. All right. And look, we don't have to plug these into any function. They give us the y value of each one. You see that? This y value is 25. This y value is 31. This one's 35, and so on. They give us the y value. So the distance, the total distance, see if I can kind of squeeze it right in here. The distance is going to be this width times this height, which is 25, plus this width times the height of this one. See, the first one was the width times this height. This rectangle is this width times this height, which is 31 times 31. And then we would just keep going, adding them up. And so plus, and then that would be what? 5 times 35. See, that's the height of the next rectangle. And we just keep going down the line. See, the height at 30, the height would be 41. So we're just going to keep going down the line. And I don't know if I'm going to fit them all on here, but let's see, that's 5 times, and then plus 5 times 43 plus 5 times 47. And I'm going to come down here plus 5 times 46 plus 5 times 41. No, we don't have that one. Okay. I'm using left endpoint, so there's the last, okay, there's the last rectangle right there at 2546, okay. Oh, I see what I did. Y'all see that? I didn't draw it right, did I? There's that, and then the height of that one. We're using the left endpoints. I had it drawn wrong. That's what it is. All right. So anyway, there it is, drawn right. Sorry about that. Okay, I messed it up. Okay, but I mean, you still get the idea. Okay, I just drew this from the wrong endpoint. I did it did it okay there. It's just this last one I messed it up, and this one. All right. But anyway, there's your answer. And so once you plug that in, you get 1135, and that is that would be feet. Okay, that's how many feet you're going. So, and of course you can take the feet and you can convert it to miles if you want to, but you know, and that sounds about right. See, basically what we're trying to get across to you here is the distance that you traveled in those 30 seconds is the area under this curve. The area under this, that's the distance you traveled, because see, this is time, and we're multiplying time times velocity, and that's going to give us the distance. All right, so I hope this helped, and sorry about the screw up right here. You know, I'm not going to redraw the whole thing or rework the whole problem just for that little piece that I drew wrong. But yeah, I hope this helped. Check out my other videos and watch the next one after this, the one that's named the definite integral. Watch that one. It'll probably be a long video, but it'll be a good one. You'll learn some stuff. All right, so hope this helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will catch y'all later.